Let's do some integral practice. Okay, so let's say we're trying to find the antiderivative for this first one, the function x plus 3 dx. So we're trying to find some function in terms of x where it'll allow us to input an x value and compute the area under a curve. So x plus 3, that function looks something like this, with an x-intercept of 3 and a slope of 1. So this x-intercept here is 3, and the rise over run is just going to be 1. And to find the area underneath, we can use geometry. So we can split this up into a rectangle like this, right, and a triangle like this. We can compute these two areas, and we can just add them up, and that's going to be our area. Except doing it with integrals is going to be a lot easier. So the antiderivative, or the integral of x plus 3 dx, okay, the indefinite integral, so there aren't any specific bounds, we're just finding a general solution. We can split this up because we know that integrals are additive, and we can use our sum and difference property, where the integral of x plus 3 dx is going to be the same as the integral of x dx plus the integral of 3 dx. So the integral with respect to x of x, that's going to be, well, right now it's x to the 1. So we want to raise that by a power of 1. So it's going to be 2 divided by the new exponent, which is 2. Okay, and then we're going to be adding, right? This right now, 3 is the same as 3x to the 0, because x to the 0 is just 1. So if we want to find out what the antiderivative of 3 is, we have to raise the exponent on the x by 1. So it's going to be 3x to the 1 divided by the new exponent, so over 1. 3x to the 1 over 1 is just 3x. So anytime we have a constant, like say 15, and we're integrating that with respect to x, say, it's always going to be that constant times x. Because according to the fundamental theorem of calculus, the derivative of this integral should give us the original function on the inside of the integrand back. So the derivative of 15x is just going to be the constant in front of the variable. So if we go the opposite way, if we integrate 15, we're going to be getting 15x. So we know that the integral is going to be x squared over 2 plus 3x. And then remember, we need this plus c here, because we don't know what the vertical shift of the function is unless we know what the function's value is evaluated at x equals 0. So this is our general solution for the indefinite integral. But what if we want to find the definite integral of the function x plus 3 from 2 to 4? So our lower bound is 2, upper bound is 4. Well, all we do is we take our function, x squared over 2 plus 3x. We don't need this plus c anymore because it's not indefinite. It's a definite integral. And we're going to evaluate that from x equals 2 to x equals 4. So this is going to be x to the 4 over 2 plus 3 times 4. And then we're going to be subtracting the same thing. Oh, this isn't, I mixed up my 4 here. So it's going to be 4 squared, right? Because 4 is our x, plus 3 times 4, minus, okay, minus 2 to the power of 2 over 2, plus 3 times 2. So we're subtracting those two things. 4 squared 16 over 2 is 8, plus 3 times 4 is 12, so it's going to be 20, minus 2 squared is 4 over 2 is 2, plus 3 times 2 is going to be 2 plus 6, so that's going to be 8. So see how these 8's cancel, and we just get 12. So this is going to be our area under the curve x plus 3 from the x values 2 to 4. And again, we can use that. We can find this answer using geometry, but calculus is a lot easier. We just use integration, substitute our values, and we're done. Okay, let's determine the indefinite integral of 2 sine x dx. So what integral property can we use for this? Well, we know that 2 sine x has a 2 in front of it. 2 is a constant. And we know our constant multiple rule, where this can be set equal to 2 times the indefinite integral of sine x. So whether the constant is inside or outside of the integral, it's still going to be able to kind of be switched up, and it's still going to be an equivalent expression. Okay, so it doesn't matter if it's on the inside or outside. Typically, it's best to just bring it on the outside and evaluate the inside of the integral after the constant's gone. So this is going to be 2 times, well, what's the integral of sine x? Okay, we know that the derivative of sine x is cos x. We know the derivative of cos x, or in other words, the second derivative, or sorry, d squared, yeah, cos x, or d squared sine x over dx squared. So the second derivative of sine x is negative sine x, and the third derivative of sine x, so if we differentiate that again, of dx cubed, that's going to be negative cos x. And if we differentiate that again, so the fourth derivative, we're eventually going to get back to positive. So that's going to be over dx to the 4. That's going to be positive sine x. So notice how, once we kind of do this cycle, if we go the other way, right, according to the fundamental theorem of calculus, if we integrate the derivative of something, we go the other way, we're going to get the derivative that's 1 degree lower. So if we go from sine x to negative cos x, that means we're taking the integral. So the derivative of sine x is just negative cos x. And remember, we're not done here. We still need this plus c. So our answer is going to be negative 2 cos x plus c. Okay, evaluate the integral from negative 1 to negative 1 of the natural log of t dt. So if we kind of envision this, right, the natural log is just a logarithm, so it's going to have a vertical asymptote at 0. I'm just going to flatten it like this. And this question actually doesn't make sense. Let's say it's from positive 1 to positive 1, because logarithms don't exist in the negative. So let's say it was from positive 1 to positive 1, right? In this case, the natural log of 1 is just 0, except we're taking the integral of the natural log. So we can't just say it's 0 right away, right? If we take the integral of this, we're saying what's the area. Actually, just to make this make more sense, I'm going to change this to maybe 5. So let's say we're trying to find the area when t, if this is our t-axis, this was the natural log of t, right? Basically what this question is saying is, what's the area underneath the curve from this point, t equals 5, to the same point, t equals 5. So notice how our bounds haven't changed. We're going from 5 to 5, which basically gives us a straight line. And the area of a straight line, right, in one dimension is just going to be 0. So remember that property of the 0 property, it was called, I guess. If our bounds are the same, the integral is always going to be equal to 0. Okay, so we don't need this plus c for this example because this is a definite integral. We have 2 distinct bounds. If the bounds weren't there, we would integrate ln t, which we don't know how to do yet, but we'll figure it out in future videos. But we'd integrate ln t, and then we would add our constant c. Okay, what's the total area represented by the integral from x equals 3 to x equals 4 of x to the 4 plus 1 dx plus the integral from 4 to 7 of x to the 4 plus 1 dx. So the integrands, the x to the 4 plus 1s on the inside, those are both the same. And notice that the 4 on the top left and the 4 on the bottom right are also the same. So remember our property we went over in the last video. This is going to be the same as the integral from 3 to 7, so the lower bound on the left to the top bound on the right, of the inside function x to the 4th plus 1 dx. Okay, so this is going to be, well, x to the fourth, the integral of that, right? So we can separate this because of this plus sign. We know that integrals are additive. So it's going to be x to the fourth dx plus the integral from 3 to 7 of just 1 dx, right? So just for sake of space, I'm just going to write that up here. This is going to be the integral from 3 to 7 of x to the fourth dx plus the integral from 3 to 7 of just dx. So what's the antiderivative of x to the fourth? Well, the antiderivative of x to the fourth is just going to be x to the fifth over 5, right? Because we're raising it to power 1 higher than it was before and dividing it by that new exponent. So it's going to be x to the power 5 over 5. And then remember, we're evaluating that from x equals 3 to x equals 7. So that's going to give us some value, some scalar quantity. And then from that, remember, we're going to be adding the integral from 3 to 7 of just 1 dx. So remember, the integral of 1, a constant, is just going to be 1x. So this is just going to be 1, or sorry, not 1. It's going to be x evaluated from 7 to 3. So if we actually plug in these values, we're going to get 7 to the power of 5 over 5 minus 3 to the power of 5 over 5. Okay, and then we're going to be adding, well, this is just going to be plus 7 minus 3, because we're just substituting in 7 and 3. And instead of 7 minus 3, I'm just going to put 4, so it's going to be plus 4. So 7 to the power of 5, let's just do that right now. 7 to the power of 5, that's going to be 16,807. So that'll be 16,807 over 5 minus 3 to the power of 5. So subtracting 3 to the power of 5, that's going to be 243 over 5. And this is going to be plus 4 here. So this is going to be, just to kind of simplify this fraction, 16,807 minus 243. So 16,564, 5, and then we can add 20, so 84 over 5. So if we made this for 20 over 4, or sorry, 16, so 4, if we want the common denominator to be 5, we'd multiply by 5 over 5, yeah. So this would be 20 over 5. So these two, oh, these were subtracting though. Yeah, so if we took 16,807, subtracted 243, we'd get 16,564, and the number we're going to be adding 20 over 5. So 16,584 over 5. Let's look at this question here. Trevor's evaluating the integral from 0 to 5 of each of the n dn. So this is an exponential here. He recognizes that according to the fundamental theorem of calculus, the value of the integral is the antiderivative of the function, right, evaluated at n equals 5, right? That's our upper bound here. The antiderivative evaluated at n equals 5 minus the antiderivative of the function evaluated at n equals 0. Okay, perfect. We just learned about the fundamental theorem of calculus. It tells us that we can have some function e to the n. If we integrate that and evaluate it with a definite integral, it's just going to be capital F of 5, right, minus capital F of 0. So these first couple sentences, they make total sense. We've been through this. He also recognized it as he integrated x to the fourth dx from 0 to 2 in a previous problem. He only needed to evaluate the antiderivative of the function at its upper bound since its lower bound was 0, and capital F of 0 is 0. Okay, so what this is saying is we're still using this fundamental theorem of calculus, right? So if we integrated x to the fourth with respect to x, this would be 1/5 x to the fifth. And if we plugged in our lower bound 0 in x, this would give us 1/5 of 0 to the 5th, which is 0, which is equal to capital F of b. And remember our fundamental theorem of calculus, capital F of a, sorry, capital F of a. So remember our fundamental theorem of calculus tells us we want to take capital F of b minus capital F of a. And if capital F of a was 0, this term goes away, and what Trevor's saying is all we need to do is evaluate the antiderivative when x equals 2. Okay, so that makes sense so far. Is Trevor correct in using this method for the exponential integral? Why or why not compute the integral's value? Okay, well, let's think about it. Let's use our fundamental theorem of calculus here. So Trevor's looking at the integral from 0 to 5 of e to the n dn. So first, let's find an expression in terms of f of b minus f of a of what that would be. So we know the derivative of e to the n, or e to the x, but right now our variable is n. That's going to be the same thing, e to the n, and we proved that previously. So if we're going the other way, if we know that the derivative of e to the n is e to the n, if we go the other way and integrate that, it's also going to be the same case where it's going to be e to the n. Okay, so this is just going to be, if Trevor has his integral from 0 to 5 of e to the n dn, this is going to be the same thing as e to the n, the antiderivative of the function itself, evaluated from 0 to 5. So this is going to be capital F of b minus capital F of a, which is equal to capital F, right? Our b is 5, minus capital F of 0. And we know our capital F function is e to the n, so this is just e to the 5 minus e to the 0. But Trevor's saying, can we use the same method and just ignore this e to the 0? Because in the last one he did, f of a was just 0. And e to the 0 is not 0. E to the 0 is 1. So we can't use the method Trevor talked about in his original integral because the function, or the function capital F evaluated at 0 is not 0. So we're not subtracting 0 from capital F of b, we're subtracting 1. So it is important, we do need to include it. So we can't just dismiss it completely, we have to do e to the 5th minus e to the 0. Okay, so e to the 5th, let me just put that in my calculator here, that's going to be 148.4 minus e to the 0, which is 1, so this is going to be 147.4. So notice how if you ignored this e to the 0, this capital F of a, or capital F of 0, you would get the wrong answer by 1 unit, right? So the real area under the curve e to the n from 0 to 5 is really 147.4 units. Okay, so there's just an example there. I hope this kind of made sense, like just getting some practice in with our, with our properties of integrals, the difference between definite and indefinite integrals, that's a big deal. So I'll be talking a lot more about integrals where we're not just using the power rule. We're going to have to use things called integration by substitution, proving different integrals, integration by parts, trig substitution, all this crazy stuff. So this is just kind of the beginning of the journey, but I'll see you in my next couple videos to kind of further your knowledge of integrals. Thanks for listening.